All right, babies, welcome to our second video lesson here on waves. What we're going to look at in this section is how to determine the speed at which a wave moves through a given medium, as well as the variables that affect the speed at which a wave moves. So obviously a wave is created by a disturbance, and we had two types of disturbances. One which creates a transverse wave where the disturbance is perpendicular to the direction the wave is going to move, and a longitudinal wave where the disturbance would be parallel to the direction of the motion. So in this case, we have just a diagram here of a transverse wave, which is, again, easier for us to analyze. So let's say I want to determine the wave speed. So speed is just, again, how fast the wave is going to move within a medium. So anytime you want to determine the speed of something, understand that speed is just very simply the distance a wave travels in a certain amount of time. Now, in terms of a wave, when we represent the distance, what we can simply do is represent distance in terms of the wavelength. Again, the wavelength is, obviously the length of a complete wave. It's the distance from point to identical point on consecutive waves. But it gives us a way to measure the distance, because obviously here, if I look at, my waves that I would have here a complete wave right here, and then I would form another complete wave. So I would have two complete waves in that distance, which in this case looks like 10 meters, and it travels a time of 4 seconds. But when thinking about it, what I can break that down to is the wavelength. So in terms of the distance we're going to relate to the wavelength of the wave, okay? And then time obviously is the amount of seconds that it takes to get from one point to the next. And what we can relate time to is the frequency. And we can look at, okay, based on the movement of a wave, how many waves do I have in that given amount of time? So in this case, in that 4 seconds, I have two complete waves that are shown in there. So in terms of the speed of a wave, to kind of relate it to its own variables, since that wave is moving through medium, that the speed of any sort of wave can be found by the frequency times the wavelength. So know that V stands for speed measured in meters per second. F is the frequency of that wave measured in hertz. And again, as a review, hertz represents, again, the number of waves in a given amount of time, so waves per second. And wavelength is obviously the distance between two identical points or the length of one complete wave. So think of this as the length per wave. Now, unit-wise, just to show you guys, what we have here is frequency times wavelength. So I have waves per second, if you think about that. And then I would have times my distance, which would be meters per wave. So dimensionally, this ends up becoming meters per second. The waves on top and waves on bottom would end up canceling each other out. So this just again shows that in terms of our variables, we're looking at frequency and wavelength, that if we just simply multiply those two things, we should be able to find how fast a wave is moving through a medium. All right, so our first example here, we're going to use that wave speed equation. So V equals frequency times our wavelength to determine the speed of waves. So our first example here, we have a wavelength of 2 meters and a frequency of 0.25 hertz. So if I want to find the speed, I'm just going to take my frequency of 0.25 and multiply it by my wavelength of 2. Simplifying that, I'm going to get a speed of 0.5 meters per second as the wave speed. All right, now, next example, again, frequency and wavelength, so equation-wise, not the most difficult thing to do. Just going to give you some different values. So here my frequency is 0.0625 hertz, and I'm going to multiply that by 8 meters. So you notice here the wavelength got longer, and at the same time, the frequency got less. So multiplying those two things together, I will get, again, a wave speed of 0.5 meters per second. So you'll notice here I get the same speed. So what's going on is, because I see here my wavelength got longer, as the wavelength gets longer, the frequency actually gets much smaller, but notice it keeps the speed the same. So let's see what goes on in this last example. Wavelength is 4 meters, frequency is 0.125. So if I want to calculate the speed, I'm just going to take my frequency and multiply it by my wavelength. And again, that's going to give me a speed of 0.5 meters per second. So notice in all three of these cases, I'm getting the same speed. Now, why is that the case? I notice this is three different examples using different numbers, and I'm getting the same value every time. Okay, the reason is, all right, so again, the speed of the wave can be determined at any point based on its frequency and wavelength. However, how fast a wave travels or is traveling is not necessarily dependent on the frequency and the wavelength. Okay? The speed of a wave is strictly dependent upon the medium it's traveling through. For example, a sound wave. Sound is going to travel differently in air than it would in water, than it would through a solid. It is the material itself, what the wave is actually traveling through, that is going to dictate how fast the wave is actually moving. So there are two variables, and this equation shows, and we're going to talk about how to use this equation. This equation is showing two things. It's the tension force. So Ft, tension force, think back to forces. Tension, think of like springs or strings, just how much you're pulling on something. So the best way to represent this may be through like a spring. So let's say that I have a very just simple spring, though the coils are really tight or close together. So in this case, since a spring, think about as I stretch a spring, they're going to get further apart. So this would be a very loose spring. Versus if I take that same spring and also now stretch it out. Okay? In order to stretch a spring out, that's going to require more tension. So what this equation tells me is that there's two things. You have the tension force on top of this fraction. So the tension force has a direct relationship to the speed. Direct meaning that whatever I do to the tension force, it's going to do a very similar thing to the speed. Now the second thing is this Greek letter mu. Now this is a little bit sassy because we've seen this before, but this Greek letter mu represents the density. So the density represents how tightly packed the medium is, meaning how close are the particles of that medium to each other. So I can relate this back to the spring. While this one right here on the top has a low tension, and this one on the bottom has a high tension, okay? In terms of density, the one that has low tension, this will also be more dense, okay? And this one down here will be less dense. Now, how the heck do I know if it's more dense or less dense? Is because of the particles. Notice the coils in the spring. There are more coils in this length of spring than there are down here. Here there will be less coils. So this would be more dense and less dense. And like I said, this sort of spring that's not as tightly wound up and not as stretched out, the speed's going to be much slower. Okay, so this one in the end would have a slow speed versus on the bottom, this one would be a faster speed. So this is an inverse relationship in terms of the density, that the more dense something is, the slower the wave is going to go. So this is an inverse relationship. Now, how does this work then? So you'll notice around this, there's that big square root, and this is where it gets a little confusing. So for example, if I were to make this thing in terms of like, let's say the tension, let's say that I were to make this thing 4 times bigger in terms of the tension. I pull this thing with 4 times more force. What that's going to do is that is going to, based on this relationship, it is going to increase the speed. Let me go back and use a different color here. That is going to increase the speed. Okay. Now, because there's a square root around this, when the tension is 4 times bigger, I'm going to take the square root of 4, which gives me 2. So that means my speed is going to increase by a factor of 2 times. Okay, so it's still going to be that direct relationship, but whatever that number is, we're going to have to square root it. And it's the same thing with density. Now, density is a little bit different because it's an inverse relationship. So let's say I make the density 4 times bigger. Well, what that means is since it's an inverse relationship, I'm going to see a decrease in the speed. And again, because it's a square root, I would also take the square root of that 4, which means then that my speed is going to be 2 times smaller. So it's density and tension that are going to determine how fast a wave moves through any given medium. Now, to show this to you, because I know it's hard to understand what is tension, what is density, I have a little video here for you. I know it's a little bit small, but this individual, it's a little bit over-exaggerated, but put an iPhone inside of a guitar as he was strumming the strings. Now, the purpose of this is to show what happens between not only the tension, but the density. So you'll see here the thickness of the string. So notice if you ever played a string instrument or know of it, this is obviously the string You have it, this would be more dense because it's a thicker spring. This would be less dense, okay? So we got the density going on. And as well, those of you who have played guitar know that you have to tune a string. By tuning a string, by the way, side note, you can't tune a fish, but you can certainly tune a piano. But nevertheless, to tune a string, for those of you who have played it, you know there's a knob that you would turn. And in order to tune a string to get to the right note, you actually increase or decrease the tension of the string. So you have the thickness and the tension that you can control. And what that does is it creates different sounds and different waves. So I want you to recognize in this video not only the differences in the strings, but also the differences in terms of the wavelength and frequency you're going to see within those individual strings. Beautiful. I'll stop it right there. Kind of a good pause there, but notice how some of the differences, again, we have the differences in the strings, but now also look at this and be the next point. Notice this string up here where you have the thickness a lot thicker. You're going to see it's a longer wavelength, and at the same time, the ones down towards the bottom, you should have seen a shorter wavelength, but you also should have seen that while it had a shorter wavelength, you saw more complete waves. All right, so a couple points off of that. So in any given medium, the wave speed is always going to be constant. So the wave speed is going to depend on those two things. All right, not that I expect you to do the math with this equation, but I want you to know there's those two things, tension and density. As the cop rolls past, thank you, sir, for your service. So we got two things. You have tension and density. So the medium, these two things are going to determine what the medium is and how fast the speed of that wave is going to be. The wave is always going to travel in that medium. As long as it's the same, it's going to travel at the same speed. Okay? And then the second thing I want you to notice from that little video I showed you with the guitar strings is that there is also, while the wave is moving at a constant speed, there is a relationship between frequency and wavelength. That if something has a longer wavelength, it normally has a smaller frequency. And if it has a shorter wavelength, it's going to have a greater frequency. So kind of going back to the examples we did here, remember that in this example, we got a wave speed equal to 0.5 both times. So here, the speed was constant, right? It was the same speed both times, but I want you to recognize here the difference. This one, in terms of wavelength, we see that it is 4 times greater wavelength. Now, where did I get the numbers here for frequency? While the wavelength is 4 times greater, what ends up happening is that these are dividing by 4. The frequency becomes 4 times less. So another key detail is that there is an inverse relationship between wavelength and frequency. So while the wave speed is always going to be constant in a medium, frequency and wavelength will have this inverse relationship. Whereas one gets bigger, the other will get smaller to make sure our speed stays constant. To show you this relationship, just another little video here for you. So this is a video, again, of just waves on a spring. But you'll see here in the middle that there is a point where there's going to be a little bit of a change. So I want you to just, again, identify what's going on. Notice here on the right side, you have a higher frequency, smaller wavelength. And then as it goes through in slow motion here on the left side, you're going to see longer wavelength and therefore smaller frequency. So again, I want you to see that relationship between frequency and wavelength while it moves through a medium. Okay? All right, now we're going to tie all these things together with frequency, wavelength, speed, as well as tension and density. So we have a wave here. So I have my wave, and notice that within this wave, I have two complete waves, okay? And it says here that I want to know which diagram below, okay, is going to represent my wave when I now have 1/4 the tension. So what we're going to do is we're going to relate the two equations, frequency times wavelength, but as well as the square root of tension divided by density. Okay? Now the key thing here is that the frequency is going to stay the same. Okay? So what happens here is we are changing the tension. And what we're doing is we're making the tension 1/4 as big. So what we said here is that for tension, that there's a direct relationship. So if I make the tension 1/4, 1/4 is a fraction, which means I'm decreasing it. So that means if I'm decreasing the tension, that should cause a decrease in the speed. Okay? Now, what does that mean? Well, if the tension is being decreased by 1/4, the speed is going to decrease by the square root of 1/4. Now, just think of that as the square root of 4. The square root of 4 is going to be 1/2, which means that my speed is going to be half as fast. Now, what we're going to do is we're going to relate this to which of these three diagrams would that represent. So what I have here is half the speed. So if my speed is cut in half and my frequency is staying the same, what we're going to do is relate that to the wavelength. So if my frequency stays the same, in order for my speed to change, I would need to cut my wavelength in half. So in this set right here, I had 2 complete waves. So that means if my wavelength is cut in half, I need a smaller wavelength. So instead of 2 complete waves, I should see 4 complete waves. So in this case, that diagram would represent what would happen if I were to change the tension of my string. A little bit sassy, but again, it's connecting all those variables. So the tension is going to affect the speed, and then that speed is going to dictate the relationship between frequency and wavelength. All right, last example here. So in this case, we're going to do the same thing. We're going to look at our 2 equations, our wave speed, which is frequency times wavelength. But again, the speed is going to depend on the tension of that medium as well as the density of that medium. So in this case, it says we're going to keep the same frequency, just like we did before, okay? But now we're going to look at what happens when we take the density. In this case, we're going to have 4 times the density, okay? So 4 times the density means this, that if I'm going to make this density right here 4 times bigger, okay, so I'm going to make this 4 times bigger. Since density is in the denominator, so since I'm increasing the density, what that's going to do is it's going to cause a decrease in the speed. Okay, it's an inverse relationship. Now, because of the square root, if it's 4 times more dense, that means my speed is going to be 2 times bigger. Okay, so think about over here, my wave speed is going to become 2 times bigger. Now, since my frequency is staying the same, that means my wavelength then would have to be 2 times longer in order to create that speed. So since here I have 2 waves, think of this as 1 wave, I need to make that twice as big. So twice as big, again, would be represented by this last diagram here. So these last 2 examples are a little confusing, but again, we're looking at that wave speed equation, frequency times wavelength, but really what it really depends on is the medium. So we have the tension of the medium and the density, which dictate the speed, but then we see that inverse relationship between frequency and wavelength that dictate that constant speed as the wave moves through that medium. So if you guys got any questions, jot those things down. We'll see you next time. Good luck. Peace out.